Hi, and welcome to Data Science in Industry vlog. My name is Konrad Wojdan, and today I would like to tell you what it's like to work as a data scientist, especially data scientist in industry. So, first of all, you have to be a detective, data detective. And this is a very interesting part of being a data scientist. You need to formulate hypotheses, deeply understand the problem that you need to solve. What is the real need of the customer, of your business partner or scientific partner? Maybe you should help them to formulate this need sometimes. And moreover, you need to really feel and understand the nature of industrial process you are modeling. So you will have to read a lot, sometimes books, sometimes scientific articles, to understand how the underground gas storage operates, how the power plant operates, what are the physics behind the district heating network. But of course, reading is not enough. First of all, you will talk to people, different kind of people. You will talk with operators, with dispatchers, with automation guys. You will talk with managers, sometimes with scientists from universities, because you need to understand the physics and the business model related with the industrial process. And of course, if you need to talk to people, especially in some remote places, it means that you will probably have a lot of delegations, which is also, I think, a good thing. You have an opportunity not only to meet interesting people, sometimes very good experts in control systems, in some device operations, but also you will be able to visit new places, which is also a very nice thing to do. And because you are a detective, you will never be bored in this career path. Moreover, you don't need to, you should not be afraid of mathematics. The mathematics is here to help you. This is the tool that you can use to solve the identified problem. But in order to use this mathematics, you need to be a software developer. Maybe not, a software developer who code business applications. Rather, a software developer who knows how to use mathematics, some dedicated packages. Probably you will write a lot of scripts, maybe a bit of object-oriented programming. Your primary tools would be probably Python and R, maybe Julia or other dedicated programming languages. Sometimes, if your data scientist, if your, let's say, AI algorithm operates as a part of the bigger platform, IT platform, you will need to pack your algorithm within a dedicated API. So you should know how to talk with software teams to decide about the optimal API. So I hope that you can see that this is really a career path that lets you do very interesting things. There is no place for boring. You have to learn new things every day. So I encourage you to become a data scientist, especially the data scientist that operates in industry. Now I would like to show you some use cases from, let's say, the Industry 4.0 perspective. As a data scientist, you will be able to do the forecasting algorithms. You can forecast, you can predict the demand for let's say, electricity, energy, for heat consumption, for gas consumption, etc., etc. You can sometimes for let's say key products from plants and factories you are working on. Sometimes this is the crucial input for the optimization algorithm. If you would like to optimize the operation of intelligent buildings, you have to predict the number of people in this building for let's say today, tomorrow, maybe a month, depending on the optimization horizon. You can also predict production, let's say for instance production of energy from renewable energy sources. You can predict prices, like now this is the hot topic, the gas prices, especially for projects where you're operating more in the business layer. As I told you, those forecasts are usually, but not always, of course, but usually the inputs to the optimization problems, to optimization tasks, where you would like to optimize usually complex industrial systems. What I mean by complex, I mean the processes with high number of decision variables, outputs, disturbances. Sometimes with long response time, so you need to plan ahead, make your decision, keeping in mind that those decisions will have an impact to the future, in the future. For such systems, there is usually a need for optimization, right? If you do not only react to what you see, but you need to consider many aspects of a process, many devices, many business goals, then there is a space for optimization. And I think those are the most interesting projects, the projects for big boys, where you have to combine predictive models with the upper layer of optimization algorithm, sometimes with the utilization of algorithm that forecasts the final product of a plant or factory. For instance, the heat demand, right? The optimization is an art of simplification. So you cannot focus on all the aspects of the process, whether it's the power plant or the district cooling network. You have to focus and first of all identify the most crucial aspects of this process and make models. Someone can call it digital twins of the crucial interaction between those parameters in the process that has a relation with optimization goals, like, I don't know, minimization of emissions, maximization of efficiency, right? And that have a link to, so you also need to focus on parameters that have a link to constraints identified during the, let's say, detective mode phase of a project. We can usually those processes are so complex that we have to try to split the whole task into smaller pieces. For instance, let us assume that we have a district heating network and CHP plants that provide heat to the network. So if we want to optimize such a big complex system, that consists of hundreds of thousands or thousands of heating substations, few heat sources like CHP plants or other renewable sources as well. Let's say that have a accumulator, heat accumulator within it, in it. This is a complex system. So let's try to start with some basic things we can improve. Usually it's the control system that is not well tuned, but let's skip it for now. Let us assume that the control system is well tuned, and on top of it we can try to identify the first thing that we can optimize. Let it be the efficiency of the power boiler in the CHP plant. Let's try to do it. In such case, we will focus on devices that provides air and fuel to the boiler. We will focus on efficiency parameters like temperatures, like CO emission, like the amount of oxygen that goes to the air via stack. So we'll be focused on a narrow aspect of this whole network, which is a power boiler. And in this case, let's say we can call it the first layer of optimization. We will have to create this way or another the model of a power boiler in order to predict how our decisions related with, let's say, fuel and air distribution will affect things, parameters like temperatures that has an effect on efficiency, or CO or NOx emission that also affects our business. And we can apply the algorithm that will constantly in the loop get the feedback from reality, and based on this feedback the algorithm will try to propose better decisions and send those decisions into the control system. There are many approaches to this problem. In the next videos I will show you one of them. In this layer we have to repeatedly send the decisions every few minutes or even tens of seconds. So we have to act fast, focusing on a small piece of this whole district heating network, which is a power boiler. But we can also think about the second layer of optimization, which is the optimization of the CHP operation. So we have to decide which boiler to use, which turbine to use, what should be the load of each boiler and turbine. So this is, let's say, an economic balancing, economic load dispatching. And here we can consider that single boilers are already optimized by our algorithm. So they have, let's say, optimal efficiency characteristics. Now we should focus on a different aspect about optimal load dispatching. We have to look further in the future because of the long time related with the boiler startup. So probably in this layer we have to consider 24 hours ahead. Our decisions doesn't have to be sent to the control systems every, let's say, minute. We can assume that sending those decisions every 15 minutes or every half an hour will be fine. We don't even have to send those decisions to the control system. Maybe it can be a recommendation for operators, for dispatchers, how to operate the plant. And when we have CHP plant optimized, every CHP plant that is plugged to the district heating network, then we can think about the whole network. Oh, by the way, maybe this CHP plant has a heat accumulator. Then we can combine the task of economic load dispatching with the task of optimal utilization of the heat accumulator, which makes the task even more interesting. So later, the last layer is the layer of the whole network. Here we can focus on helping dispatchers decide which CHP plant to use, what should be the temperature of the supply water, what should be the pressure of the supply water, how to use a pumping station if in the district heating network in order to deliver proper amount of heat to end user. So it's a different kind of tasks Here the heat demand forecast that is calculated by the separate algorithm can be very helpful. Dynamics of a system here is counted in hours, sometimes days. In case of big district heating networks, the decision about the supply temperature has enough in a single CHP plant has an effect on the return temperature of the water that comes back to the CHP plant after even 48 hours, sometimes during the summertime when the flows are lower. In this last layer, where you're considering the whole network, of course, you can assume that the characteristics of single CHP plants are optimal because lower layers of optimizers are operating there. So one way is to take the whole task and solve it at once, but a better approach is to simply decompose it and simplify it to smaller pieces, to smaller tasks that are organized in, let's say, layers. Here you can see another use cases related with the optimization. We can try, those are examples from real life projects. For instance, we can try to answer the question, what is the optimal schedule of compressors utilization in the underground gas storage? So when to start each compressor, when to stop it, in which mode each compressor should operate. Another example is to, for instance, how to adjust fans and feeder roads in the power plant, and how to adjust the opening of auxiliary air dampers in order to maximize combustion process efficiency and minimize emissions for the current value of disturbances like the unit load, like the coal quality, if the fuel is the coal, of course. Another example, what should be the number of running pumps in the pumping station for the current or assumed flow and pressure parameters. We can consider also the energetic clusters and try to optimize its operation. The cluster usually consists of can consist of solar panels, wind farms, maybe a CHP plant related with the district heating network. Maybe there is an energy storage, maybe there is a service called demand side management, where the users get the reward if they will not use the electricity. And this is a complex system once again, right? So there's also a space for optimization. And once again, it's hard to cover all the physics, all the aspects of the process. there is for sure a space for machine learning approach that simplifies some relations, and it really helps. It really helps to combine the domain knowledge with the machine learning tools. This combination is a key to success. I will talk about this later on. So, as you can see, in order to optimize industrial processes, we need to have prediction models of an optimized system, of a combustion process, of the flow, pressure, and temperature distribution in the desiccating network, etc. What are the desired properties of such a model? First of all, if you want to use it for the optimization purposes, it must be fast and as simple as possible, because it will be used many times before we find the optimal solution. It would be great if it has a form that allows us to calculate derivatives, because derivatives show us the direction, where is the optimal solution, how to approach this optimal point. And from the business perspective, it should be easy to maintain and tune, because we hope as a data scientists that it will work for a long time for a particular customer or business partner. It would be great if it will have some auto-adaptation methods, because the environment is changing, devices are changing, the law is also changing, so it would be great if we can adapt to those changes, if the model that is used in the optimization task can adapt to those changes. We also should have the access to most recent data, because the most recent data are our feedback from reality. But we need to trust those data, so we should apply validation module that detects missing data or some goofy data that we cannot trust. We can try to apply the anomaly detection algorithm to find suspicious portions of data. If there are some missing value and we are optimizing that daily operation of those plants, we need to have a way for filling the missing values, or if the number of missing value is too high, we can just say game over message to the user, but we of course trying to avoid this. If the portion of missing data is not huge, then we can try to give the good estimate of what is missing. And like I said before, optionally we can have a module that will adapt our models to most recent system behavior. If the new type of fuel will be used, maybe some devices will be replaced. Of course, it will generate new data. In this case, the model will not be up to date anymore, but it's great if there are some mechanisms that allow us to easily update the model, maybe in automatic way. The data science tools can also help to detect anomalies in industrial processes. For instance, we can find out that something is wrong with the compressor or with the pump. There is a strange behavior of a chiller. The oil temperature is too high in this turbine. Those are things that we can detect using the anomaly detection algorithms. But detecting anomaly is just one step. The next one is detecting states that leads to the failure. In short or in long term, this is the holy grail, right? In Industry 4.0, that you would like to detect the process states that will end up with a failure. For instance, in the short term, we can say that there is a high risk of compressor failure in the next hour, and we can give an advice to switch to another compressor if there is one available. Or in case of a power plant, we can give an advice that the pulverizer, the coal mill, is overloaded. There is too much coal in the mill. So we can give the recommendation to the operator to reduce the feeder speed. Or we can do it automatically if there is a connection between our AI algorithm and the control system. In case of a long term, we can help to to maintain the system. That is why the failure prediction is the part of the predictive maintenance strategy. Because, for instance, we can give the hint which pipes should be replaced during the summertime in the district heating network, because those pipes have the highest risk of a failure, and this failure will be associated with a high cost. We can check which, for instance, pumps need to be replaced, or at least the serviceman needs to look at those pumps with the highest priority, because otherwise it will be broken within the next 3 months. So as I said, there is a phrase called predictive maintenance in this Industry 4.0 concept, and generally this is the optimization of the maintenance policy that is based on prediction of failures. So I hope that now you have a feeling of what kind of problems you will solve as a data scientist that operates in industry. All of them are very interesting. My top one is the optimization task, because there you have to combine all the things that I have mentioned into one bigger project. You will meet a lot of interesting people. You will acquire a lot of knowledge about the processes that you're dealing with. So generally speaking, it's lots of fun, and on the other hand, you can help the environment, because your algorithm can try to minimize efficiency of harmful gases. You can also minimize the harmful impact of the plants or factories on the environment, because we'll just increase the efficiency of the process. If we increase the efficiency of the power plant, we need to use less coal to produce the same amount of energy. So I recommend you this path of career, and I hope we can meet in data science meetups maybe next year or even this year. See you.